Hi, I'm Eyal, and good day everyone, and welcome to today's web session, Keeping Your Latency SLAs No Matter What. My team and I help prospecting customers migrate from different platforms into Scylla on a daily basis. We help prospects and users of Scylla to size their clusters properly and most efficiently. Our team understands the provisioning a database correctly, remove future challenges, and also control the latencies, and allow the builders of the application to spend more time on their business needs rather than talk about, challenging those latencies. So let's talk about latencies and why they happen. In some cases, latencies is considered a necessity or an evil necessity of a system building. There are multiple sources of latencies in every system, more so in a computerized system such as Scylla. Sources can range from hardware components to bad programming and all in between. The questions sometimes are overlooked is why should you care about database latencies, and people are getting them as granted. So the first thing you should look at is, for example, the user experience. In many cases, we see users complacent with 50 or 60 milliseconds of average latency. It means that the 95 percentile is most likely way, way above 100 milliseconds. And we are familiar with the note that 100 millisecond delay in response time will cause user attrition from a website or reduce sales convergence in an e-commerce website by dozens of percentage points. It means latency costs you money. There is even more critical items that, not just losing or getting a better user experience. For example, if you think about it, if you're using a database as a control system, in a control system, the database part is part of the feedback loop in that control system. It means that any shock resolution that you need to put through the system is dependent on the database speed response. If the database latency becomes the major component of the ability of the system to stabilize, that can challenge your system stabilization over time. And let's talk about liability. Let's say you have an IoT use case. Data is stored for analysis and audit capabilities. If your database misses one sensor entry, it might not have any impact on your liability. However, if your database has prolonged increased latency to the point that mutations are no longer recorded, you might be liable for missing crucial data points for posterity, which in turn put your organization liable for missing, for example, an alarm on a crossing temperature bar in a boiler, on increased pressure in a turbine steam pipe. Those liabilities as part of your control system. So now that we understand that latency should be accounted for in our design, let's understand the sources of latency in a database. So we would like to understand the systematic sources of latency in a database system. So let's start with the obvious one, hardware. Many practitioners will start, rightfully so, with the hardware component and settings to mitigate latency issues. The first candidate for improvement for any data persistent system will be the media which we store data into. If you're trying to use, for example, slow spindle disk to store data, be aware that simple one block seek time will exceed 6 milliseconds, which means there is no chance you'll hit the sub-millisecond bar for your 90 percentile metric. And I would argue probably your 75 percentile will be higher than 15 to 20 milliseconds. By now, you might be sure that using SSD is the great idea to solve that problem. And you are mostly right. However, there are some points we need to check about your SSD construction. For example, what is the maximum concurrency capabilities in that specific SSD? Are you using RAID controller that might add substantial latency to your overall system? If you are planning on placing your SSDs, for example, on a network attached storage solution, be aware that the max throughput and accrued latency over the network is also have to be accounted in your budget of latencies. Another item that many users are overlooking is the buffering capabilities of any media type. If the buffering solution existing in your SSDs, it can hide latency in the form of long waits for your time-sensitive transaction, which somehow, and most likely will happen, stand behind a large data transfer. In such case, the large, most likely the less important data transfer can easily add 5 to 10 milliseconds to your highly valuable data persistence or retrieval. So your database application should control that buffering capability that your media has. Next in line is your network configuration. First, look at your application user's location. Placing the application server near the users is an obvious requirement. However, do not compromise on the database location. Do not place your database instances far away from your application. Network latency will pile up on every query you'll be doing on your system. And if the database servers are far away from the application server, you'll end up with extreme latency numbers. In some cases, we see usage of, for example, unnecessary data routing. For example, do you really need the full coherent data persistent on every transaction? In some cases, you will tell me, hey, I need that, and that's fine. But in many cases, this is totally redundant. Data coherency comes at a cost. Data needs to reach every node, and the nodes need to acknowledge, for example, those writes. So each replica adds latency to the overall time the client is waiting for the data persistency to happen. Next item I would like to talk about is your network technology. I'm going to say a phrase. Commodity hardware does not mean you should use bad hardware. We are in 2020. Networking technology used by server vendors most commonly is a 10 gigabit network or higher, where 25, 50, and even 100 and 200 gigabit per second throughputs are not a rare case. So do not overlook the network technology. Ask your infrastructure team to provide good hardware specs, locations close to your application, and consider your consistency strategy. The cost of good network is not higher than a bad one, and this is a choice you can actually make. Let's talk about our compute resources. Every transactions translate to multiple compute operations. Building a system that uses limited number of CPUs will cause delays in data processing. Users should look into, for example, CPU allocations in a virtualized environment. Deploying a database on a virtualized system such as VMware or OpenStack are common enough. Users deploying database instances need to make sure the CPU and memory over subscription are not including or accruing latencies into the database response. Let me give you an example. On a VMware system with a 6-to-1 oversubscription, you will commit 6 virtual CPUs to a single physical one. While it might sound like a great idea to increase CPU utilization when you deploy an application server, for example, for a database operations, that need for every millisecond will sacrifice your latency. So to suffice the data movement, you must have the actual CPU tuned into your virtual CPU. Also, same goes for the memory of a subscription. Do not oversubscribe your database nodes. Such approach can be very harmful for your deployments. Until now, we spoke about the hardware. Let's talk about the database architecture. Let's look at the contribution of those architectures into our tail end latencies. The first point we are going to look at is primary-secondary architecture. While reads in most primary-secondary architecture can be served from both the primary and the secondary nodes, write are a different story. Writes must be committed by the primary node, which means that one of the nodes that, for example, the write node is clogged, your queries will start piling up at the gates of that node. And as expected, your latency will as well go up to unbounded numbers. Yes, I know it is possible to shard your data, but now we are introducing an additional layer of complexity. And the data sharding will force your application to basically parse the data and decide which shard should be handling which part of the information, which again, at the end of the day, will increase your latency will include more latency into your system. The next thing we're going to talk about the single-threaded database. As you know, as a complete data path is handled by a single resource, this case you will be serializing the data structure, and the impact on latency can be, again, harmful and can cause transactions which should have been processed in record times start lagging behind. Users are deploying mostly single-threaded databases in large numbers to overcome that serialization challenge. While doing so, the implementers are introducing, for example, new challenges. First of all is system complexity. More processes to manage and maintain, which increase your labor into making sure that you have a working system. Second, most of those database systems that are single-threaded are cache databases, or memory first, we call them. In such case, using a cache database system is augmenting, in many cases, a persistent layer that is standing behind. And once again, introducing latencies in a case of, for example, cache misses, as the cache miss needs to be retrieved from the persistent layer back to the cache, back to the client, which again, getting new data into the cache layer will give you penalties on the latency sides. And for databases that uses software virtual machines, giving the I/O, memory, and CPU control to a third party might sound like a good idea to minimize the effort on your development cycles. But yet again, it comes at a cost, the latency cost. Users of database like Cassandra are familiar with garbage collections process. The JVM is now clearing up memory, so the application cannot make any progress. For a low latency database like such poses are devastating. Not only you stop the current operation, but now the system is starting to build backlog, which will need to be cleared. So you're starting to put yourself in that vicious cycle of pausing to clear memory in order to get new application, new workload, and starting again. In addition, in addition to those uncontrolled pauses on operations, the JVM is limited in its ability to support modern size hardware. There is a point in which the JVM is no longer effective in managing CPU, I/O, and/or memory resources. Yet again, inherently building latency into the system. Let's take an example. A JVM is bounded to a certain amount of memory it can handle. Most likely what you will see in the JVM setting is somewhere between 48, 64 gigabytes. That is the reason that you will see, again, limited, if any, actual data caching in the database layer. It means that your reads of data will come from a slow media you have attached to the server, to that server. Be it, for example, an SSD or a Spindle, it is still a magnitude slower than the memory latency that you can actually get from indirect memory access. But it's not only the quote-unquote external forces that determine your latencies. We, the users, or the guys who write the application, have a significant part in the latency creation as well. Data modeling has a tremendous impact on your latency. I will enumerate a few of them, but by all means, this is not an exhaustive list of reasons you will be able to build latency into your system. So those are the things that we mainly see, but there is tons of more, and we can definitely discuss them later in this session. Let's start with the most obvious one, hot partitions. Hot partitions are caused when your application is targeting the same datum time after time. Since in most databases, the access to that datum is based on a selection or declaration of a partition key, accessing the same partition key can cause traffic jam when looking to write to that specific partition. Hot partitions are caused mainly due to low cardinality in your data model. For example, selecting gender as a partition key. It means that you will be selecting less than a handful of options. In most cases, only 3, male, female, and undefined. It means you're gonna put, for example, the population of the world, 7 billion people, on only 3 partitions. Accessing to that specific partition time after time will force the database to bring billions of records for no good reason. Next would be the full table scans. Do you really need to fetch all this data from all these billions of records from the table. In most cases, we find this is not the case. And user then take the data and filter it in the application layer after making basically the database sweat and execute a pile of unnecessary queries. If you still need to do full table scans, there are efficient ways to do so. Each database has an indexing or a hashing algorithm by which the data is being distributed inside the system. Make sure your table scans adhere to the way data is actually hashed or organized inside the cluster. That will minimize the latency and the data round trips you're going to be doing. As I just mentioned, data is sorted. Still, we see users sort data by what we call the default characteristics of the data type. For example, an alphabetical ascending, and then querying the data in the reverse way, from Z to A. At that point, your database engine has to scan the record from the end, going backward to the beginning for no good reason, while the actual data might be at the first point of accessing that you get to. But last, if you are using a geo-replicated system, querying data from the far end of your system will not be fast. That one I can guarantee. Make sure you set the application to query the local replicas of your data before trying to get data from the far end if something happened. Next, I would like to tell you about Scylla's design decision, how they help reduce your tail end latencies. But first, if you can help me with a short poll to better understand how database latencies impact your organization. Okay, so we have a poll there, and I'll be very happy if you can start punching your numbers. So what is the expected data size in terms of terabytes, before your application, in your application? Thinking about the amount of data you have in the cluster actually give you the ability to understand what can be your, for example, the sizing of it, and that sizing will actually impact your latencies. So feel free to put your answers in. Thank you very much for your answers. And again, how many operations you're doing? What is your throughput looks like? The throughput has a tremendous impact also on latency. Think about it as a demand and supply curve that you have. The higher the throughput is, the latency will be higher as well, because you will have to start putting in more and more resources to get those transactions going. And that will eventually give us the ability to understand what is your target latencies. And then what is your 99th percentile write latencies that you need to adhere to? This is 100% a business decision. You have to tell, the business have to tell you what is your 99 percentile looks like. It will determine your cost, it will determine your system, it will determine your data model. Because if you cannot adhere to those latencies, you will not be able to suffice your business needs. Same thing for the reads. Actually, it's in many cases more crucial than the writes. And if you think about it, latency is also tied to the size of your transaction. So if you're going to try to write 1 gigabyte of data, that's going to take a certain amount of time. But if you're going to try to write 500 bytes, that's going to take a completely different time to get that information. And the last but not least is where you actually deploy your clusters. We find out that there are differences between the different cloud vendors, as well as if you're doing it on-premise. And I'm going to talk to those points as well during this session as well. I'll give you guys another minute or two just to digest those 6 questions, and thank you for your responsiveness, much appreciated. Okay, I'm gonna end the poll in 30 seconds. Oh, okay, that's great. Jay did it for me. So let's go and talk about how we solve things with Scylla. So again, thank you for your answers. If you have attended one of our latest series of workshops, you might have seen the next 3 to 4 slides, so bear a second with me. If you have not attended the workshops, I highly recommend you do so. Those are a twice a week, once every 2 weeks workshop that we cover how to deploy Scylla, data modeling in a nutshell, and more. So please register. I think that we'll have some links in the chat, so you can just go onto our website and subscribe for the next workshop. So let me dive into how we actually solve the issues with latency. So first, we took away any third-party organization from controlling the system. Using a closer to the hardware programming language provides us a faster and more efficient use of our modern hardware. So we wrote Scylla in a C++, which gives us a lot of powers. They give us the advantage of basically unlimited resources that we have in a server. And we are not gonna be limited by a middle tier framework like the JVM, which cannot handle the abundance of those resources that we have. Using C++ gives us also the ability to put Scylla in user space memory and control other peripheral resources such as your disk, your network, and the CPU in a way that is not limited by anything. We can actually get anything, any resources that we want from the system directly from the user space using our C++ programming. Next, and very important, is our shard per core architecture. Other systems use system scheduler to design and assign data to processes, which means that one thread can clog the whole system and never let other threads utilize that specific system. As you can see on the left-hand side, that nice puppy is just munching on the data and not letting anybody else do that. That's your typical system using the operating system scheduler. Using a shard per core architecture allows Scylla to parallelize these operations. It means that each of our shards is responsible for a certain amount of data. And one shard cannot obscure the system to other shards, as each shard gets its own fair share of system resources, meaning he gets an equal size of memory, an equal size of CPUs, and an equal size of I/O capabilities. And I'm going to talk about it, how we do that in a second. This is how Scylla achieves basically unlimited throughput. We are limited only by the actual amount of CPUs you're going to give us and your disk ability to process and deliver data to your users. Next, forget about massive trial and errors of settings day in and day out, trying to get your workload tuned to your system. Scylla deploys a continuous memory allocation to be used as a caching system for your application. You do not need to tune these memory settings for a specific use case, and it's auto-tune itself. It is there for your actual users every time you read data from your system. The caching system in Scylla will cache both keys and data rows in the available space. In most cases, we will allocate roughly 50% of your server memory to be used as caches. The next point we're going to look at is your disk or your media capabilities. Scylla, when it's installed, will benchmark your disk system to make sure that this system cannot introduce uncontrolled latencies or throughput limitations. For example, we make sure that Scylla utilizes the disk system without any disk or file system buffering. Since Scylla makes sure that any buffering happens inside Scylla and not in the disk system, we control those buffers. Once those buffers are set properly, Scylla can allocate the appropriate disk access for each one of those workloads. For example, data writes and reads initiated from the user application should have precedence over any backend office processes that Scylla might need to perform. We will see a little bit more in the next slide. Scylla self-optimizes itself to these use cases. Since we know the performance capabilities of the system we are using, remember, we benchmark those, Scylla was able to monitor backend processes and make sure memory flushes and compactions are controlled and do not cause any latency spikes in access to the data, like the disk, the network, the CPU, and providing a very clear and direct path for your application query, commit log, or repair process directly to the user. The internal controls we have will provide the front-end workloads over precedence over the backend workloads to make sure that Scylla provides the best latency to the user side. Scylla looks not only on the server side, but also on the client interaction. And we introduce now a shardware drivers. Using our optimized drivers guarantee a client query hits directly to the shard responsible for that partition, which makes sure we get the best latency out of it and less routing of data, either internally on the server or in the entire cluster, which again reduces the latency that you're gonna be accruing. And we have optimized drivers for Go, Python, and Java, and we continue to develop more and more drivers for those use cases. So how does customer actually solve latency issues? We have over 60 use cases, which we show tremendous latency and very good latency reductions. We show performance stabilization and cost control on a database deployment. I encourage you to visit our website and read the blogs, see the videos, and learn about the use cases that is basically closest to your heart or line of business. I will focus on one of them. I will focus on the Comcast one. So this is what the users tells us about the deployment of Scylla. Reducing latencies on all metrics by 95%. Now, I know it sounds fantastic. It sounds almost unreal, but those are the numbers. And let me show you how we did that. Comcast started with over 900 Cassandra nodes. The first interaction we had with the Comcast team was about controlling the tail end latency. The 99, 95 percentiles were horrible. As you can see in the charts below, the red bars represent writes and read latencies of 90 percentile, 99, and 99.9 for the Cassandra deployments. The Comcast team even used caching system in front of their Cassandra deployment to reduce the read latency. It helped for the average latency, but still for over 10% of the read queries, the latencies are not in the acceptable range for a modern application. A read latency higher than 60 milliseconds for 1% of the users, when you deal with millions and millions of users, it means that thousands of users and applications are degraded to the point of not being able to use them. That latency translates to an overhead on the company's support and call centers. So it costs you money. So when transitioned to Scylla, we were able to reduce the latencies to less than 10 milliseconds for the 99.9%, both reads and writes. The story is not complete without mentioning the following 2 points. One, Scylla performed under 300% higher write throughput and 20% higher read throughput. So not only we reduced the latency, we actually increased the amount of users that could interact with the system. We also reduced the hardware node count from over 900 nodes to less than 18 nodes in total for Scylla. So again, reduction of 90% in node count, which means smaller operations overhead, easier upgrades, and efficient scaling if and when needed. If you want to hear more about the Comcast use case, again, go to our website. There is links to both the chat, the blogs, and the videos. I think we're actually going to post the links to those as well on the chat window here. So, and we will email those into the webinar after the webinar. Okay, so hey, we want to have the recipe of doing the same thing for our use case as well. So let's see how we can do that. Size your application properly. That's the first step. Okay. Talk to your business team. Collect the business needs and requirements. It will help you to size the system properly. We have done several webinars on sizing, and it will be a good idea to start there to find the right information you need to collect from your business side. Think about high availability. We see and learn time after time that high availability requirements can be crucial in understanding the adherence to the latency budget. Again, we need the balance between the physics of orchestrating a system versus the high availability requirements and the latency budget we are working with. You can test you can test your application performance with different tools as well. You can create your own data model and benchmark it towards a database. And I can tell you there are test drives in different databases and applications. And many database vendors, including us, provides test drives and free trials for database, to, as a service even, for your convenience. So please make sure you subscribe to those initiatives, as they will provide you with a fast and easy way to learn about your application interaction with latency, throughput, and the system itself. Again, think about the different metrics that you have to adhere to, and make sure you have a balance between all three of them. So high availability is important, but the question is, what's going to be the impact of that high availability? For example, if you're going to do an each quorum writes, you're going to have to wait for those queries to come in from the far end of your system. Now, the next thing you're going to have to talk about is your hardware. Select non-blocking building blocks. It's so easy to basically go into a route that will limit you at the end. Again, oversubscribing in a virtualized system, you have to think about those items. You have to understand exactly what is going to be the hardware you're going to be provided with in your system. Make sure you get the right understanding of the different components. You should have ample amount of CPUs. Modern CPUs comes in abundance in today's servers. We have seen servers with 40 and 60 and even more physical CPUs in each box. There is enough memory. We like servers that have a lot of memory, so we can have that caching layer available for you as a user for your read workloads. We like those fast NVMe-based storage that are available in a relative reasonable price to be used. Think about it. A simple SSD can do around 500 megabytes per second. In terms of IOPS, we're talking about anywhere between 50,000 to 300,000 IOPS per second. If you go for an NVMe based, you're talking about 2 gigabytes, like 4 times higher, 2 gigabytes of throughput, and 4 times higher on the IOPS. And the delta on the price is not 4x, it's much less than that. So in terms of cost performance, you'll be much better off using those great hardware settings that are available today. Now, if you are on infrastructure as a service, think about AWS, GCP, Azure, Ocean, all those cloud vendors, they have NVMe-based instances. I know some people would recommend you do not use those ephemeral storage capabilities, and I would tell, use them. There is a reason you're using a replication factor. There is a reason you have a backup and restore capabilities. There is a reason why you do a multi-geo. And on the cost side, you will get the same benefit. While on the throughput and latency side, you will get a magnitude size higher throughput and lower latency using those NVMe-based instances. So don't be afraid of them. Another item we'll see from people think, hey, what happens if I lose a node and I have to restruct it? If you look at all those instances that the infrastructure as a service provide, they have amazing and very, very efficient networking protocols and networking cards inside of them. They will provide you those 10 gigabit, 25 and 50 gigabit per second throughputs, and Scylla can utilize those. Scylla can take advantage of that throughput and stream in and stream out data from your nodes to rebuild should you lose a node and need to replace it. If you are using an on-prem system, let's focus on your disk and network bandwidth. Don't fall into the trap of using a 1 gigabit network. Also, on the media side, what we see in many on-prem deployments, people will opt in for the network attached storage. There is nothing wrong with network attached storage, but we do ask that you understand exactly how much IOPS and throughput is provisioned for your system. There is a crucial point where that network attached storage can harm your throughput and your latencies, because again, you have to go over the network, and if you're bounded by that storage system, it's going to directly bound your latency numbers. So again, keep an eye on those, make sure you size it properly, make sure you have good connection, good understanding with your system architects to get the right information about those storage systems. Let's talk about data modeling. We talked about partition key entropy. You have to make sure that data is well distributed inside the cluster. We have done a great webinar about data modeling, and we will paste the link to that webinar, and I would highly recommend, if you're a developer, start there. That's the point you want to start to look at Scylla. You want to understand how data modeling is impacting your capabilities. So make sure your partition key is well defined. If you need to do bucketing, if you need to make sure that you have the limited amount of storage or limited amount of data in each one of those partitions, that you slice that information properly. Think about query design. Think about those full table scans. Think about those reverse queries. Think about, are you using a token-aware client? Are you actually going to the right token to get the information? Think about, for example, using prepared statements. We see those systems that you're using, and sometimes we are amazed. Those are small changes you can take and get an amazing and a very impactful latency reduction by just changing one way you interact with the database. If you have not yet seen that, check our monitoring system. Our monitoring system have a dashboard that is just for your CQL and just for your data model capabilities. You will see there, for example, if you're doing something called allow filtering, you might not be aware that you're doing a full table scan. For example, if you're using a Spark application, Spark sometimes will send something called allow filtering, meaning it's going to try to filter the information or try to get information from your database, not based on your partition key. By then, he needs to go and override the indexing system to retrieve the information from the database. Make sure that you understand those queries and the source of those queries. So the dashboard will tell you exactly those queries coming from. Make sure that you are using prepared statement. Prepared statement saves a lot of CPU from the server side. You take that query that you want to do, maybe it's a repetitive query, you send it once to the server will cache that query, and the next time you have to use it, you don't have to send the server the whole query. You just send him the hash information for that specific query, and then the server side does not have to parse the query, does not have to understand if it's legal or not. You just have to parse the data you sent along with it. Again, saves a lot of CPU time, saves a lot of latency headaches for your application. Again, monitoring. Look at your logs from your application. Look at the logs from Scylla. Scylla will tell you, for example, if you're using huge partitions. Sometimes in logs, we see people who are using millions of rows per partition. That's not efficient. Make sure you parse those logs, make sure you understand what's going on there. Sometimes you'll see compacting huge partition. If you have a partition that is 2 GB in size, we want to know about it. We want to make sure that you understand that you actually need that partition, and maybe you can actually reduce that size of partition to make it more efficient on your client side to parse and get the information. Again, it translates to latency. This is crucial for anybody who's deploying any database out there. To summarize, we can control latencies. Control latencies is possible, okay? It does involve that developers, DevOps, business side, and system operators need to collaborate. You need to talk to each other. You need to understand exactly how you want the system to operate, how you expect the system to operate. Your architecture, the database architecture, and the system architecture will impact your tail end latencies. There is no other way. Yes, I can get 50% latencies on every system to look the same. However, what does the tail latency will tell you about your system? This is your user experience. If 1 out of 10 the queries I'm sending from my mobile phone end up not getting me the information, I'm not going to be a happy user. And you want to make sure that the 10% of your users are still happy every day and every hour. And again, there are low-hanging fruits you can look at right now. Data modeling easy to change in most cases. Definitely something like prepared statement or reverse queries or using a token-aware driver. Those are rather easy to change, and you can do that today. Nothing prevents you from doing that. And we have talked about those. There are excellent materials on Scylla's website and webinars you can look at. Look at your traffic patterns. Are you, for example, doing cross DC queries? Do you really need them? If you don't, eliminate those and make sure that you're using the local queries going in. Again, those are low-hanging fruits. If, for example, changing from quorum to local quorum will change the whole picture of your settings. Test drive your application. Going again, this is a crucial point. Make sure you understand the sources of latencies. Make sure that you understand the latency and you are agreeing that that's the latency you expected to get. So you can test drive your application. Go to our website, you can test drive your application right now. Take the application, you'll get instances of Scylla, and you can see, okay, this is the impact I'm gonna get. If you go onto Scylla Cloud or Scylla Cloud Your account, you can actually deploy the cluster, bring on and get the full monitoring stack into your eyes and understand where are the patterns that you have to deal with in terms of latencies. And with that, I'm completing my talk and I will jump into the Q&A. So let me get the Q&A stuff here. Okay. Let's see, what do we have here? Okay. Let's start with the first one. Okay. 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 How do you know what is a large partition? How can I find out where is that large partition in my tables? Okay. So if there are large partitions, in most cases, there is a metric you can set inside Scylla to tell you, okay, after I'm compacting, during the compaction process, if the compaction process is compacting a partition that is, I think, higher than 100 megabytes, it will print it into the logs. In that case, it will tell you exactly which table has that partition, and you'll get the token number of that partition. You can go and retrieve the information using the token information from that system to get it out of that system and understand where is that large partition and where is it coming from in the table. The second thing is, how does the application throughput impact latency? Is there a difference between read and write throughput impact on latency? The answer to that is yes. The application throughput impact latency. There is no other way. And it, again, looks like it can look like a hockey stick. If you are going to an unbounded throughput, your latency will accrue along the way of that increase on throughput. So you have to understand what is your throughput and what is your latency. And you will design your system to meet exactly for that throughput plus some additional margins, what is the latency you can get here. You might be okay, say, hey, maybe I'm getting 2 times higher the throughput, I'm okay in getting another 50% in the latency numbers. And again, you control it. Think about controlling the latency. That's what you want to do. You don't want to have any surprises along the way. So if you see your throughput going up, you most likely have to understand what that throughput causes to your system. For example, if you have a higher read throughput, I would advise that you want to increase the amount of cache or the memory you have in the server. You might not need more CPU or more disk size because you don't grow the data, you just grew up the throughput. So increase the memory only and that will suffice. On the right side, if your throughput goes up and the latency go up as well, maybe we are challenging the throughput of the media. Maybe we're using a slow SSDs or, for example, some type of network attached storage in our instance, and we will be better off moving for an ephemeral storage and then getting control of the latency while maintaining the higher throughput capabilities. The other question, does Scylla support splitting log partition? We don't split automatically split log partition, sorry. What we do, we'll print the information about those large partitions and let you decide what you want to do. What I will tell you then is, hey, is there a reason for the large partition? Sometimes we see the large partition is actually not used. For example, it's some kind of a test or a bot that created a huge partition in your data model, which you did not expect. So what we'll tell you, hey, look, if you need that partition, if you do need those partitions and you have oversized your partition size, we'll talk about, for example, bucketing or salting those partition keys to make sure they are reduced in size and get better throughput and lower latencies. Is throttling a rate of requests from client to server needed? Is it possible for Scylla to buffer requests? So Scylla does buffer some of the requests, but those buffers, as expected, are limited in size. It's not indefinite size of buffer. If you are overriding those buffers, what's going to happen is that Scylla will basically throttle down or tell you in the client side, hey, you're oversubscribing the system in terms of throughput, so we'll push back. What you will see it in the application log, you will see it in the monitoring system, you will see basically queries that were not responded, and we'll ask you to do one of the things, either reduce the amount of throughput coming from the client, most likely you don't like that answer, or you will be asked to add more resources. If we'll see that you are maxing out on the CPU, add more CPU. If you're maxing out on the IO, we'll ask you to add more IO throughput. In many cases, the memory will not be part of this request capabilities unless it's 100% read workload. Another one is, can you reach the single-digit millisecond latency for every use case out there? We are building, we're building a user-facing application on GCP, and would like to make sure the application is able to maintain sub 10 milliseconds for every transaction. So we did something similar with Comcast, sub 10 millisecond latencies for the 99 percentile. That was the target, and that's what we built there. You can do it with any infrastructure as a service system. What we'll ask you to provide us is, hey, what is the throughput you have in mind? Second, on GCP, you have multiple options of media. You can use the persistent drives. You can use the NVMe attached systems. And then we can know, for example, if you have a low throughput, maybe you can go along with the persistent drive, it's going to be still fine. But if you need a higher throughput, because the persistent drive, for example, are limited to a couple of dozens of thousands of IOPS per second, so we'll ask you to go with the NVMe, which will provide you the latency you're looking for. Yes, we can build a use case, and we can build a system that will adhere to that 10 millisecond latencies on the 99, 95 percentile. Again, you have to decide that sub 10 millisecond latency, where is the bar setting? Where is the limit that you want to go for? Is it the 99 percentile? Is it 95? Maybe it's the average. Average is fairly easy to get. As you go to the right-hand side to the 95, 99 millisecond, then it becomes a little bit more challenging and will require you to invest more in the hardware settings to get that information out. Okay, does Scylla support full table scans using Kubernetes containers? Are there optimized drivers besides Spark to handle parallel scans on the same table based on separate keys? So I'm going to start with the Kubernetes side. We have a Kubernetes operator in beta today. So yes, we support Kubernetes. It's not related to the full table scans. You can do full table scans with Spark. There are optimized drivers it's the Java driver. You can use it for Spark and handle parallel scans on the same table based on separate keys. You can run multiple scans on the same table from different clients. It's the concurrency capabilities you're going to have inside your system. I will put one caveat here, is that in Kubernetes, I would highly recommend you go again on our website and read about the cost of containerization. There is cost in terms of latency when you use containerized system. We're not saying it can be huge, it can be 50%, but it can be as low as 3%. But then we'll ask you to tune your network, your CPU, scaling, and memory allocation in the containers to make sure we will be able to adhere to those latency numbers you're looking for. In terms of full table scans, it will become a complete application side definition. We'll, on the Spark side, for example, we'll define number of connection pools, the concurrency level, the amount of reads you're gonna do in every one of those transactions. There's a complete different settings we can talk about when you actually have to configure Spark as well. And with that, I think again, if you, somebody raised his hand, I'm going to try to see if I can see it. Let me look at this. Okay. Okay, thank you for the presentation. Okay, if you'd like our team to help you assess your system, by all means, stay in touch with us, send us an email. You can reach out to us in many ways. There is a public Slack channel. There is the mailing list. There is the website. You can ask questions about Scylla and get answers. Reach out to us when you have to build your system. We are more than happy. Please subscribe to our workshops. Again, those are an amazing way to start your journey with Scylla, and they are available every 2 weeks. And the next one is at the end of next week. So please subscribe and attend those as well. And with that, I thank you everybody for your attendance, and I'll see you in the next webinar and workshop. Thank you.